Hello everyone, this is Raj and you are watching BW Lab. In previous video, we generate a PWM signal using Xilinx block set. But you can see we have generated the PWM signal using Xilinx block set in part 1. But we will generate the same PWM signal, but in this case we generate by using Verilog code. Okay, so you can see this is the Verilog code. I will tell you what is this, all these codes are, and also in this video I will tell you how to provide a deadband between the two switches. Means if you know about the inverter or any circuit where there is a two switches. If you know about the single phase inverter where there is a two switches in a same leg. Okay, so what happens, these legs are complementary, means it means if the QH is on, then the QL should be off. Okay, and the QH is off, then the QL should be on. Okay, but as we know, in these are for ideal cases, but in non-ideal case there is a rise time and fall time in switches. So what happens, maybe it's if there is no delay between the switch on and switch off, then what happens, they may get short circuit. So what we do, we provide a dead time. So how do we provide dead time? But first of all, how do we generate PWM pulses? We have seen this, how can we generate PWM pulse. Okay, so in this case, as you can see, in this case I have a counter and the counter value is 4000. How do we decide these values? I have told you in part 1 video, you can check. And how to decide this constant value, this is also I have told you. So in this case, my switching frequency, I have taken here the counter value of 4000, that's why the switching frequency here is 25 kilohertz. Okay, and the duty cycle is 50%. I have taken 2000, so the duty cycle is 50%. We have compared this counter and constant value. Then if the counter value is greater than the constant value, it will give a logic 1, and if the constant value is greater than, it will give a logic 0. It means this is our PWM signal. In this PWM signal, how can we provide a delay? So for this we have to use a shift register. So one shift register provide a 10 nanosecond delays. You can see we have taken 5 shift registers. Okay, it means the total delay of 15 nanoseconds I have given to my system. We can understand by this diagram. You can see this is my PWM signal, which is generated by using which is generated by comparing this counter and duty cycle. Okay, and this PWM signal is generated by providing the delay of 5 shift registers. So now how to generate the switching for my higher switch and lower switch. So as you can see, this is my PWM signal, and this is here is the 50 nanoseconds of delay, you can see. So how do we generate this pulse QH signal? By doing the AND operation, of PWM and PWM delay, I can get this Q high switch signal. So how this work, this is, suppose this is a value of 1 and this is also value of 1. Here is 0, but here is 1. In this case 1 and 0. If I do 1 and 0, then the AND gate will give me 0 value, and if there is 1 the AND will give a 1 value. Similarly here is 0. Now for low signal, how do we generate a pulse for low switch? For this we do a negative of PWM. In this case we are taking OR gate, PWM delay. We take, in this case, QL switching pulse is generated by OR operation of PWM and PWM delay, and a negative we give. Then what happens, suppose this is 1, this is 1, and this is also 1. then what happens, 1 1 is equal to 1, but I have taken here is not operation, so the value is 0. Similarly, if there is a 1 and there is 0, the value is 0. Sorry, there is 1 and 0, so the OR operation is 1 and the negative of 1 is 0. In this case you can see the value here is 0 and here 0, so 0 and 0, what, 0 and 0 is 0, so the negative of 0 is 1. Okay, so I hope you all understand. Let's move to the Vivado software for coding. Now I am opening my Vivado software. Okay, Vivado software is open. So what we do, first step is create a project. Click on next, then give the project name. I am giving pulse dot underscore db1. okay, so click on next. Do not keep unchanged these settings, RTL project, and check to the do not specify sources at this time. So now we have to choose our board, which board you are using. According to that you can choose. So first category is general purpose. Okay, and my family is RTX 7 processor I am using. In Nexus 4 board I have told you the RTX 7 is used. Okay, the package is CSG 324 and the speed is -1. So you can see there are 5 options, but in my case my FPGA is XC7A 100 TCSG 324. okay, so select it and click on next. Finish it. So you can see the Vivado is open, and this is the flow navigator, and in flow navigator there are many options. So project manager, synthesis. So we have to inside the project we have to add our sources. So add sources, there are 3 options. So add or create constraint. We are not creating constraint. The constraint will create the we will create constraint after our design source is complete. And we are not creating simulation sources, we are directly do in our hardware. So choose add or create design source. Click on next. If you have a file, then you can add file or add directories, but in my case I don't have any file, so create a new file. File name I'm giving file name same as my project, pulse underscore db1. okay, then click on OK and finish. After this they are asking for the port name for input and output. I am not giving right now, I will do later. Okay, yes. So our project is created. You can see our project is created, which is pulse underscore db1, and inside the project our design source is pulse db1.v file is created. You can see, if I zoom in, you can see time scale is given 1 nanosecond, and the rest are the details which is not required for us. You can see pulse db1 module is created. Inside this module we have to write our code. Okay, so let's start the coding. So let's do some codings. So first of all we have to assign input. What can be the input? Input is clock first, so first input is clock. Then next output, since input is over, and now we have to assign outputs. Output. So output, what do we want? So what we want in output, we want PWM signal. Okay, but here we have to add I will tell you what is this wire. So let me complete output track WM. Now what we required next. I have told you there are 2 pulses in the final output. Output is Q high, first one. Okay, and second output QL. Okay, so you can see after completing you have to give comma comma, but in last integer variable, in last variable no comma is there. If I give comma then it will show error. If I remove this, then you can see green sign, it means my code is right, there is no errors. Okay, so inputs and outputs are defined inside the bracket. Okay, and if we want to define reg type variables or wire type variables, then I have to define outside the outside these brackets. Okay, you can see. So what else we need? We need a shift register. Okay, we do not want output of shift register, we want only a reg type shift register, so that it can store the value. So okay, so reg, how many bits we want? I'm choosing here 8 bit. So from 0 to 7 it's 8 bit. Oh, shift shi, variable name is shift, and the initial value is 0. Okay, and other things are, we need counter. As we have seen, we required a counter. So counter, how many bits counter we want? 12 bits, so 11 0. So I have chosen here 12 bit counter, so no initial value required. Next, so I have told you the value 4000 and the counter value 4000. So we have to assign value of 4000 in integer. Okay, and this value is assigned in variable which name is period length. Period length is equal to how much? 4000 period length. Next, the duty cycle integer duty cycle, I am giving the name of pulse length. Pulse length. What is the value of pulse length? Pulse length value is 2000. So our input output reg type integers are defined, completely defined. But now we have to make a counter. So we have to make a counter so that it start counting from 0 to 4000, not 4000, 399 means 3999. Okay, so we have to make a loop. So how do we make loop? So always at the rate if my positive edge dg, it means in clock there is a positive edge and negative edge. If positive edge comes in clock, then the action start. Okay, so begin. So how do we generate counter? So if my counter is less than period length, you can copy from here. Period length, if period length, then begin what? Begin counter is equal to counter plus 1. It means if the period length is less than, period length means less than 0 means 0 to 0 means 1 to 4000. If means counter is less than 4000, then what happens? The counter will start counting. Okay, we started the begin, so we have to end. Now else what? Else begin. So what do we want? If my counter value is less than period, then it start counting. But if the counter value is greater than period length, then the counter should be reset. So the counter value is equal to 0. So since we have started the begin, so we have to end this, and also one more end required to end this always block. So here counter, so here it shows showing error. So okay, the counter mistake. Okay, now what we need? So what can we do? So we have to assign what? PWM. So we are assigning PWM value if not if counter is if counter less than, so we have to make comparison. We are now we are doing comparison. Okay, so first, if my counter is less than pulse length, then what it gives a value of output. If not, then the value is 0. We have made a comparator where you can see if the counter value is less than pulse length, then the value is 1. Okay, the value is 1. If not, if the counter value is not less than pulse length, then the value is 0. Till now we have generated the PWM signal. Now we have to do coding for deadband. So what can we do? So we have to make another always block, always at the rate. In this case also pose age clock, positive age of clock, begin so now shift 0 less than equal to PWM. Now we have assigned now we have assigned the PWM signal to shift register. Okay, and this shift 0 in first it means the signal is coming to the PWM signal is coming to shift first shift register. Okay, now we have to assign, now we have to shift this value to another shift register. Okay, the meaning of this code is till now the PWM is coming to the shift register. Now this and the provided a delay of 10 nanosecond, and after this sorry, here we 0, the value is 0, should be 0. Now this shift register is coming, is the output of this first shift register is input to another shift register. It means till now we have a delay of 10 nanosecond. Okay, similarly we have to make a 5 shift register, so that the total delay of we required the total delay of 50 nanosecond we can get 1 3 2. One more shifting is required. Okay, so here 3 shift 3 is assigned to 4. Okay, so we have a 5 shift register 0 to 4. Okay, so now after the delay of 50 nanosecond we want output. So delay PWM is what we have to assign the shift register 4 value to the PWM delay. Okay, so as I told you, the shift variable is reg type. Okay, so you can see shift is storing the data, so we have used here reg type. Okay, now we have to close this. And start the, as I have told you, we have to do AND operation and OR operation. So now assign QH. How can we get QH for, means how can we get the pulse for high switch? So we have to do AND operation of what? AND operation of PWM and PWM delay. Okay, and we want a PWM for Q low. Okay, so in this case we have to do a negative of OR operation, PWM or PWM delay. Okay, here showing error because here we have not provided a column and syntax. Okay, we have missed one. Now our coding is completed, and the next step we have to do is to synthesize our code. Okay, so come back to the project manager flow navigator, where you can see a project manager, IP integrator, simulation. We are not doing here simulation. RTL analysis we are not doing. So now we have to do synthesis. Okay, synthesis is completed. After synthesis and before implementation, we have to make constraints, means assign inputs and output pin to the for my FPGA. Okay, so how can we do this constraint? So as I told you, you can use this, you can make the constraint by using the add or create constraint. Okay, and I generally do not prefer to do this like this, so what so how I do. So first I schematic, first open the schematic. Okay, you can see these are the schematics and these things, and you can see I have 5 inputs and outputs. Okay, so click on in IO ports. So you can see these are the as I have done previously, we have to assign our pins. So assign these pins, you can in my case you can see these are the p modes, and the names are given according to this. We have to assign our pins. Okay, so I'm assigning QH high pulse. So we have to choose IO standard of LV CMOS 33. So every select LV MOS 33 to each pin. Now QH I am assigning QH B13. Okay, and PWM delay I am assigning PWM delay to P mode B G14. I have chosen different P modes so that I can verify, and I have chosen different P mode so that it easy to visualize. QLO I have chosen F14. PWM output I am taking PWM output from P15. I am assigning to pin mode C K2. Okay, and the clock in Nexus 4 board. In Nexus 4 board, pin is E3. Enter. Now the constraint is completed. Now save this file. Control S. Okay. Give the file name. I am giving pulse db1 xtc. Okay. Click on OK. So our constraint is completed. You can see, if you want to see the constraint file, you can see, go to the sources, and here you can see the constraint. Open this. We have created pulse db1 xdc file, so open this. Okay, so you can make this constraint file by using the add sources, then make constraint, add or constraint file, then you can write this code. Okay, so by doing this maybe some error may occur, but if you do like this, the chances of error is very less. Okay, now our constraint is completed. Now we have to do run implementation. The next step is implementation. So click on run implementation. Yes. Okay, you can see implementation is ready, and it's running. Now our implementation is completed. The next step is to generate bit stream. So generate. Okay, bit stream is generating. Now my bit stream is completed. The next step is to connect the FPGA board and program the code to the FPGA. Okay, so connect first and then open hardware manager. Now I have connected my FPGA board. So the next step is to open open hardware manager, open target, auto connect. The Xilinx FPGA is connected. As you can see here, the controller, here you can see the controller is not programmed, so we have to click on program device, click program. Now you can see our microcontroller is programmed. Okay, here you can see I have programmed my FPGA. Okay, FPGA is connected, and I have used two probes, and you can see the pulses, two pulses which is coming from FPGA. Okay, you can see two pulses are coming from FPGA. Okay, so we if we merge these two signal, so for comparing, so now we see the now we can see dead band. So I have to expand it. For if we want to see the dead band, so we have to expand it, so you can see the clear gap between the two pulses. Okay, if we want to measure, then okay, so if we expand it more, you can see the time, you can see the distance between on and off is 50 nanosecond. The time duration between the on and off is 50 nanosecond, delta t you can see 50 nanosecond. So that's how you can give the dead time between your two pulses. Okay, so that's all for now.